So hi everyone, my name is Ryan Sarhan. I'm a research assistant at the University of Kentucky. I'm going to be talking about a water reuse opportunity for Kentucky distilleries. This project was a partnership with Roger Henley at Bardstown Bourbon Company and the UK Biosystems Engineering Department. So I want to start off with the question, why is water conservation important in Kentucky? So where I'm from, in Albuquerque, New Mexico, the dry Southwest, it is very clear why it's important. We deal with frequent droughts. We water our lawns very carefully. But here it seems like there's plenty of water. So I want to talk about some of the reasons why it is important to conserve water here in Kentucky. The first being natural resource preservation. So we have freshwater supplies here in Kentucky, but we have municipalities that provide this water to distilleries. And for the case of our partner, Bardstown Bourbon Company, they didn't actually have the capacity from the municipality to provide the water that they needed. So that's when natural resource preservation becomes important. We want to make sure we have fresh, clean water. The second is energy conservation, which is more important at the city level. Every gallon of water that goes down the drain needs to be treated using electricity so that it can be clean enough to put back in the environment. Next is cost savings. As a distillery, you may pay for your water and sewer costs, which, of course, due to inflation are increasing. For Bardstown, this consists of approximately $110,000 a year associated with this water saving opportunity. But on a water level, it becomes a lot more. It's 6.9 million gallons per year that would be saved. And that's a lot of water. Could be a lot of money, especially when you factor in the amount of investment that you'd need to increase capacity of the system, when there wasn't enough water being provided by the city. And then climate resilience, it's defined as the system's ability to handle stressors due to climate change or even adverse weather events. We want to make sure that in the face of climate changes, there is still the ability in the system to provide and use that water. And then lastly, we've heard this before during the conference, corporate sustainability endeavors. I saw that the KDA and Heaven Hill both have water efficiency and water use goals associated with their work. So to put this in context of the distillery process, first we're starting with the mash. We're using city water in the mash and then getting those good sugars that the yeast crave and fermenting it, distilling it, aging it. The last step of the process is the bottling. And in order to bring the barrel proof down to what's going into the bottle, the distillery requires clean, filtered water that won't cause haze in the bottles. So Bardstown Bourbon Company uses an RO filter to provide that water that they use for diluting or proofing. This is a basic diagram of the reverse osmosis water system, or RO system. The city water comes into the system. It passes through the RO filter's semi-permeable membrane. 75% of the water gets through and is used for cutting. And then 25% of the water is called the RO concentrate, or ROC, as I'm going to refer to it. And this is what goes down the drain and is typically treated as waste. So the opportunity I'm going to talk about is the potential of using this RO concentrate in the mash and the fermentation step of the process. And as a side benefit, this would reduce the amount of city water that's used during this step of the process. So just looking very briefly at what is in this RO concentrate, it's a lot more than just normal tap water. Just looking at a couple things, the calcium hardness and magnesium hardness, about 200% of what's in tap water. What's interesting about these is that the yeast actually use these as nutrients during their growth process. So, interesting thing to consider there. So the goal of this project was to see if it was possible to reuse the ROC in the mashing step of the distillery process, so that the distillery can leverage that sustainability practice and also have the cost savings. The objectives of our research were to see which concentrations of ROC impacted the yeast. We wanted to use, the maximum concentration that didn't impact the yeast, and investigate that in a lab scale bourbon mash, and see what the growth characteristics were there. And then lastly, scale it up and see if that changed what we were finding. So we started off with very small volumes at first, 150 milliliter fermentation bottles, and in the end we scaled up to a 10-liter container. So the first objective, finding the concentrations that inhibit yeast, we used these fermentation bottles. We were doing some CO2 carbon capture unintentionally. And we screened various concentrations of ROC, and we grew the yeast in yeast media, so just the perfect food for yeast to keep it simple. We measured the CO2 production to see kind of the progress of the fermentation, and then we did high-performance liquid chromatography, or HPLC, to see what the ethanol production was after the end of the fermentation. So this is the graph of the ethanol concentration at the end of the experiment. The y-axis is the grams per liter of ethanol, and then the x-axis is the various concentrations. So really, what we found during this first phase is that we could not detect any difference in the amount of ethanol produced by yeast at any concentration of ROC. So this was really positive. It was telling us that up to 100% ROC, we really wouldn't see any problems with the yeast fermentation. And then glucose consumption was really high because it was yeast media and it was perfect for the yeast. So next, we developed a laboratory protocol for essentially creating a bourbon mash. And because we didn't find any inhibitory effects in the first part of the experiment, we just did a simplified, 0, 50%, 100% ROC. Don't worry, I'm not giving any secrets away about Bardstown's recipe. Just did a generic 75% corn, 20% rye, 5% barley mash. And then we measured CO2, glucose, maltose, ethanol, glycerol, and acetic acid. And so what we were wanting to look for here was, what are the dynamics of sugar consumption? Is it changing the final ethanol? And are we seeing any indications that the yeast are undergoing osmotic stress? So the glycerol and acetic acid is typically found when the yeast is, trying to adapt to a osmotically stressful environment. So we measured the CO2 production during this part of the experiment, and we really found no to very slight differences in the CO2 production rate between the three concentrations. You could say that the 100% ROC, the fermentation maybe progressed a little slower if you measure it using CO2. But CO2 is only part of the story. For every molecule of glucose, produce 2 molecules of CO2 and 2 of ethanol. So looking at the ethanol yields from this, we weren't really seeing any difference as well. We did see, looking at the time that each sample reached its maximum ethanol concentration, we did see that for the samples that contained reverse osmosis concentrate, that it was slightly later. So we're kind of seeing a little bit of evidence that the ROC is extending the fermentation time, but only slightly. Looking at the glycerol and acetic acid concentrations, again, we're not seeing any evidence that there's any osmotic stress happening with the yeast. The last experiment we did was scaling it up. We used a bioreactor in the lab at UK, And we used 100% tap water or 0% ROC. And then we chose 80% ROC because it kind of represents the maximum amount of ROC that a distillery could conceivably recycle. In a distillery setting, they would, or at least at Bardstown, they would be reusing their back set, what comes out of the still in their fermentation. So this would be 20% back set, 80% ROC. Our bioreactor had temperature and agitation control, which was really nice because it allowed us to mimic the process control at the distillery. It allows us to collect continuous measurements of pH, temperature, and dissolved oxygen. And here's what we found. So left-hand side is the ethanol concentration, and then right-hand side is the glycerol and acetic acid concentration. So for ethanol, again, we did not find any difference, which is a positive sign. And then same goes for glycerol and acetic acid. Really good news that we're not finding any differences here. And we're also seeing a similar result that the maximum ethanol concentration was reached earlier for tap water, later for the ROC. And then another note is that during the first 24 hours of the fermentation, tap water had a higher productivity, volumetric productivity, so indicating that was fermenting slightly faster for that first 24 hours. I added this slide in yesterday. We did some scanning electron microscopy of the yeast that we exposed to ROC for an hour. And what we were wanting to see here is, did we observe any changes to the yeast cell morphology? Was it shrinking? Was it crenating? But really, comparing this to the images we took of the control, there were no differences in morphology. So the takeaways here is that we didn't find any difference between using up to 100% ROC in the mash, even up to 100%. We did see some slight indications that the ROC increased fermentation time. And I'm sure at a distillery, time is money, so this could be something to consider. But any differences were very slight. And then lastly, we weren't able to find any evidence that the yeast, when grown in the ROC, were undergoing osmotic stress. So in the future, the next steps for this research, we want to look into line scaling. Does using the ROC cause scaling in piping and tanks? At least during the experiments, after I autoclaved the yeast media, the bottle would be completely cloudy because all of the hardness just came out of solution. So that's definitely something to consider here. Another consideration is, does using the ROC cause any positive or negative changes to the sensory characteristics of the final product? And then lastly, we want to see how this actually works in a distillery setting. So, potential partnership opportunity if anyone's interested. So yeah, thank you to everyone. Thank you to my co-authors and to the folks that helped me at UK.